Oh, yeah. I'm sure there's
Something on air.
Yeah, okay.
We're on air.
So does it actually, does it have anything to register that is picking up audio? But I'll assume that it's working. Yeah.
Well, welcome everyone. This is really our first formal talk of the program, even though we had a seminar yesterday for an hour or so. So our first speaker is going to be Erick Rogers, and Erick's at NRL, which is the Naval Research Laboratory in Stennis Space Centre. And apparently Erick was saying that there are 3 separate NRLs across the states, one in Monterey, one in the Stennis Space Centre, and one in Washington. And as I say, Erick's at the Stennis Space Centre one. So Erick did his undergraduate years at Clemson University, which is in South Carolina, and he studied engineering, and specifically he was in the School of Civil Engineering, but specialised in coastal engineering. And from there he went to work for NRL, firstly as a consultant in 1996, and then subsequently was taken on the establishment in about the year 2000, and he's been there ever since. So I won't read out the title, but that's what Erick's going to talk about today. And it's part of a program that's supported by the Office of Naval Research in the States, a program that involves about 20 or 30 people, and the basic idea is to look at wave ice interaction in the Arctic and how they're affecting changes to the Arctic sea ice. So Erick, over to you.
All right, and before I go to the next slide, you can read the title, but I want to mention by name the co-authors, Jim Thomson, Haley Shen. Haley will be here next month, I believe. Martin Doble, Peter Wadhams, who is a Cambridge employee, as it turns out, and Cheng, who is one of Haley's students, and he'll be here next week. Okay, so as Vernon mentioned, there are 3 different primary locations for NRL, just to explain where I'm from. So I work in Mississippi, and that's where our oceanographers are primarily. And the main campus is in DC, but the oceanography and meteorology are at different locations in order to be co-located with their operational partner. So our operational partner is the Naval Oceanographic Office, and for the meteorologist, their operational partner is Fleet Numerical, which is sometimes pronounced FINMOC for short. And now I want to talk a little bit about wave modeling, and so there's some interesting history to this. So the French actually claimed to be the first ones to do wave forecasting, and that was in the teens, the 1910 to 1920, that era, and it was actually also for Northwest Africa. And I agree with the French that what they were doing was a forecast. Basically, they were looking at a meteorological event on the chart, but it was a probabilistic comparison or evaluation that, okay, because there's this wind event, there's going to be a swell event that's associated with it. So it was a forecast, but it wasn't really a model. And the first forecast that I would consider to be a model was actually developed by Walter Monk and Harold Sverdrup. And if anyone's interested in reading about that, this is a very nice paper discussing it. And so there's a little bit of uncertainty about when the first wave model was applied. They definitely had it ready for the torch landings that occurred in the early part of the American involvement in the Second World War, but we don't know if it was actually applied. It definitely was applied for the D-Day landing, and this was a model using simple relations associated with wind speed and fetch, the size of the storm, etc., to produce a wave prediction. And of course, things have gotten more complicated since then. And so the reason we run the wave models is to improve our planning capabilities, predict waves in the surf zone and offshore, for example, when they're transferring material from one ship to another, or to route around wave events that would hinder what they're trying to do on the ships. And so, as I mentioned before, there are two operational centers. They actually both run wave models because the Navy hasn't decided quite yet if waves are meteorology or oceanography. So they just run it at both centers. They're sorting that out now with the reorganization that's going on right now. The Naval Research Lab, the last bullet there, so we're not operational. So if you call us at 3 in the morning on a Sunday, we're not going to pick up the phone because we're not there, whereas the 24/7 guys will. So we do the R&D to improve these technologies that are used in the wave forecast. And this is an example of a wave forecast. This is one produced by Fleet Numerical. And so this is standard type of plot. So the colors are showing indicating the wave height, and the arrows are indicating the wave direction. So those are two of the three main parameters that are used in forecasts. The other one being the peak period, because even though these models produce wave spectra, as I'll explain later, it's too much information typically for operational customer. So the models that we use are so-called phase average models, meaning that they're not actually tracking individual waves, but they're dealing with wave spectra. And there are three well-known models that fall into this category: WAM, WAVEWATCH III, and SWAN. And they had their origins in the WAM group, which existed in the 1980s, which is a community effort led by Coleman, Hasselman, and others. And so it has all of the kinematics that are possible to determine using a phase average model. For example, the effects of currents, bathymetry. They have a term for great circle propagation, which is actually dependent on the grid projection that's used, and the other kinematics have been added, but that varies by model. And in terms of dynamics, we have a generation of energy from wind, wave dissipation from steepness limited braking, nonlinear interactions, and again, there are a lot of extras that vary by the model. And so this is the governing equation, and so Vernon wrote a simplified form of this equation. So the one that Vernon wrote yesterday is the equation if you assume that there's no spatial variation in the velocities, but it's basically the transport equation. So C here is the propagation speed, N is the wave spectrum, so it's called the wave action density as opposed to the wave energy density, but it's basically the wave energy density divided by the relative frequency. So that's the thing that we're trying to solve for. And so it's time rate of change plus advection, and then on the right-hand side we have the dynamics, the source sink terms. And the equation is extremely simple. I think between ocean, ice, atmosphere, and waves, this is by far the simplest governing equation. But the complication comes in from the fact that we have so many dimensions. We have wave number or wave frequency, we have wave direction, so that these two constitute the spectrum. We have X and Y and time, and so the model has to integrate over these 5 dimensions in order to determine the wave forecast. And so this is just to give an example of how wave spectra are typically plotted. So as a function of frequency and direction, or they can be plotted as where distance from the center is indicating the wave frequency, and then the direction is indicated by the azimuth on the plot, and usually in convention of the direction from a meteorological convention. And so the inputs, I'm not going to read through this, but it's quite a lot. At the very minimum, you need the wind at 10 meters, you need ice concentration. If you're not in an enclosed sea, if you're receiving swell from outside your grid, you need boundary forcing, and of course, you need bathymetry. And so there's quite a few user settings that can be changed. Of course, the idea, the concept with these models is we don't like to change settings going from one region to another, because the physics should be the same regardless of where you are in the world. The only things that should change are the forcing that you give it. And the outputs they seem to have grown exponentially in the context of WAVEWATCH III over the years. Particularly the French group have been adding a lot of new parameters. So I already mentioned like significant wave height and mean wave direction, peak period, and you have less obvious output things like that we have now. It's not even on the list because it's so new. The momentum flux from the waves to the ice, the energy flux associated with dissipation by interaction with sea ice, Stokes drift, Stokes spectrum, et cetera, et cetera. So to get into the discussion of the Arctic and ice a little further, I'll preface it by mentioning one of the main motivations behind the ONR project that Ron had mentioned earlier. So this is the sea state experiment, as Ron said. And so one of the main motivations is, of course, the reduction in sea ice in the last 2 or 3 decades. And this is from an analysis by Sharon Stammerjohn, and it's showing the study area. So our cruise track is shown in black here, so that's from the 2015 cruise that I'll be talking about. It is what it's showing here is that between 1975 and 2015, you had a loss of a day per year at either end of the ice season. So, and that's actually rounding down. So you actually have more than 2 days lost from the ice season per year during that period. And a little more background on this field experiment. So it was on the Sekuliak, which is a ship that's operated by the University of Alaska Fairbanks and administered by the National Science Foundation. Relatively new ship, much newer than pretty much every ship that's used for these types of experiments nowadays. It was a 6-week cruise, so relatively long, with a lot of organizations involved, including University of Washington, Texas, Naval Postgraduate School, Woods Hole, Colorado, Cambridge University via Peter Wadhams and his student Robin, and of course NRL, Clarkson, JPL, Miami, and NOAA. And a lot of these institutions will be represented during this program in the coming months. And the experiment included a huge number of types of measurements. Remote sensing was used quite a lot from the ship every day, and we had moorings that were deployed. One of the moorings was deployed during the experiment. There were AUVs, and there was a glider that was deployed, or actually the glider was picked up during the experiment, sorry. CTDs, we did a record-breaking number of CTDs from the back of the ship, ice mass buoys UAVs, which is a short name for basically a scientific drone. And so even though, as I said, the ice is reducing year to year, it doesn't reduce in a monotonic sense. It still advances in the fall, fortunately, and that's the season that we were out there. So this is just a plot made by Jim Thomson, and it's showing the ice concentration at the start of the cruise and at the end of the cruise. And you can see that a large portion of this area filled in with ice. And it seems that if you can see, these are the bathymetry contours. It seems to fill in associated with the what passes for a continental shelf there.
And what does the color mean?
The color is the ice concentration. So it's just the deep purple is 100% ice coverage, and then the yellow and blue are partial coverage by ice.
And what's white?
White means open water.
Or land?
Yeah, whatever that is, that's land. Okay, and so I'm going to be talking about what Martin Doble and I have been referring to as the flagship wave experiment of the entire cruise. So this is the wave experiment where we got the largest waves, and it was starting around October 11th, and it is so right here. So this is the map of ice concentration from 0 to 1 on October 11th from the size analysis done by the Navy, and the white is the ship track, and this is where the wave experiment was. And the waves are coming from the southeast, and the waves were primarily measured using drifting buoys. There are actually 3 different types of drifting buoys that were used during the wave experiment from 3 different organizations. And excuse me, this is just showing one of the 3. So this is the Swift buoy that was engineered by the University of Washington APL, and is a spar type buoy, and it has most notably, at least for this presentation, it has a wave measuring system on it, it has a camera on it, and it has ADCP. So I'll be talking about data from all 3 of those. And so these are the significant wave heights measured by these drifting buoys during the experiment. And so the wind and the waves are from the southeast, so you can see that the drifting buoys are drifting toward the northwest over the course of about 3 days. And so this distance is about 120 kilometers. And so as you saw in 1 or 2 slides back, the ice edge was initially right here at the southeast edge of the transect. The ice retreated toward the northwest over the course of the experiment. Now this is from actually a separate wave experiment, but I thought it's too fun to not show. But it's basically explaining how pancakes are formed. So the Swift buoy has a camera on it. This is from October 26. Well, okay, it's not working as very well on this this laptop. But so it's over the course of the day. You see, it's basically grease ice. Then you start seeing these features within the water, and those are embryonic pancakes. And then they start forming a more noticeable shapes than pancakes. You can definitely see that, those circular shapes. And they start maturing into thicker pancakes. And it's getting toward the end of the day. And you can see that the motion of the pancakes is quite a bit less, and presumably that's associated with damping of the waves by the ice. But the pancakes are becoming so large now that they're actually rafting over each other toward the end of the day. So that's just the course of one day of how pancakes are formed. One interesting thing here, and Pat, you can chime in here if I'm wrong, but so the medium that those pancakes are floating in, it's dark. So it's either just water or it's grease ice. So grease ice is another name for having just a very thin layer of frazil ice. So frazil ice are just tiny little particles of ice, but if it's very thin, it looks dark because you can see right through it to the ocean. But it is noticeably different in appearance from the open water. But when you see a picture like this, you can't really tell, because the way you can tell the difference between grease and open water is primarily from the texture of the ocean, because it looks artificially smooth when there's grease ice on it, and that's why they call it grease. Now this is actually from that flagship wave experiment. So this is different, and that's why I was talking about frazil ice. So the normal scenario for how what frazil ice does is it collects, it adheres either to the top or to the bottom, depending on who you ask, of these pancakes, and it makes the pancakes thicker. But when the water is in a steady motion, constantly working, they don't stick as much, and so that frazil ice, it just gets thicker and thicker. So you notice in that video that that medium that the pancakes are floating in is a lighter texture, and that's because the frazil is much thicker than it was in the previous movie.
So what's the wave amplitude there?
Well, so the wave height is
Wave height.
is 4 meters. The amplitude is 2 meters.
But
Yeah.
isn't that why it's been created by the ship?
Sorry.
They're very,
I'm just wondering if they're
Yeah.
feeling some of that. Why it was being
So-
created by the ship.
It's a good question. So that breaking is associated with the ship.
Yeah.
These waves are not.
No, yeah.
Yeah.
but they're very disordered.
Well,
They're in many directions.
It's because you got your nose in it. You know, if you stand back, it looks more orderly.
Okay.
Yeah. Okay, so as I said, that is a governing equation, and as I mentioned before, right-hand side sort of sync terms, and so with the traditional before we got involved in this wave ice business, the dissipation terms were associated with white capping, bottom friction, non-breaking dissipation. So this is, for example, by turbulence in the water, which can dissipate swell energy. Of course, you have nonlinear actions. We had dissipation by mud in WAVEWATCH III before we had ice. And so the ice is the new one, but it's really not new anymore. It's maybe 4 or 5 years old. So let's say it's relatively new. And one of the things that we agreed upon when we started this DRI is that this ice source function should be treated in a holistic sense to include a lot of different mechanisms for dissipation, or I should say attenuation of wave energy by sea ice. And one way to break it into groups is to consider it as either being conservative or non-conservative. So conservative would be a scattering of the wave, so it's just redistributing the wave energy within the spectrum without dissipating it. Whereas non-conservative would be a dissipation. They both constitute what we call attenuation, because as along the original axis of wave propagation, the wave amplitude is decreasing, so it's attenuating, but it's not necessarily dissipating. So just a quick, simple review of the different theories. So one idea for the dissipation of wave energy by the ice is that it could be associated with friction at the interface between the ice and the waters, and which generates turbulent eddies underneath the ice layer, and so that would transition into heat within the water, and so that's sometimes modeled with a simple elastic layer of ice on the top. So all of the dissipation occurs in the water column, because elastic ice by itself won't give you dissipation. Another way of doing it is using discrete flow theory, and so this is one of these conservative ones where the wave train encounters discrete flows. Of course, as Vernon mentioned yesterday, WAVEWATCH III has no concept of individual flows like this, but you could give it information about flows in a parametric sense. For example, you give it a probability distribution function for the flow sizes and even flow thicknesses if you want a two-dimensional distribution. And that will give you the scattering redistribution of energy within the spectrum. And so the third one that I'm going to talk about is the so-called continuum theory. So this one is advocated by Haley Shen at Clarkson University. And so basically she took three separate concepts for how to treat ice as a continuous layer within a model like this. One is thin elastic plate, one is the mass loading model, and one is the viscous layer model. So she combines them all into one dispersion relation. So what you do is you calculate a imaginary wave number where the real part of the wave number gives you the change to the wavelength, and then the imaginary part gives you the dissipation rate. And that's basically a viscoelastic model, and sometimes it's referred to as a VE model for short. And so that we gave that the designation IC3, so if I accidentally refer to it by shorthand, that's what I mean. And it's just one of several ice formulations that we've implemented into WAVEWATCH III, so we're up to IC5 now. And for each one, there's actually multiple subsets. So if we actually wanted to, we could break it up into 1 through 8 now, and plus a scattering. There's one for scattering as well. And so these use the ice concentration and the ice thickness, which are conveniently available from a model like SICE. Effective viscosity and effective modulus of elasticity, fortunately not provided by the ice model. And of course the density of the ice can be ingested by the model, and that also affects the ice formulation. And so while I was on the ship, I was using polar stereographic grids, or irregular grids. One of them is polar stereographic, the other one is one that I came up with myself based on great circles. But the important point here is that when we do modeling at very high latitudes, we have a special challenge that we didn't have before with wave modeling, where we could use regular grids. Going into the high latitudes where the meridians converge toward the pole, it becomes very expensive to use regular grids, because the Courant stability becomes a problem as those meridians converge toward essentially zero at the pole, the delta latitude. So the irregular grids, they circumvent this problem, and so that's what we used here. And so these grids are the ones I used on the ship, but I just wanted to mention that once I got back to the office, I had access to more powerful computers. So updated it to new grids with resolution of 10 kilometers and 5 kilometers. So the original strategy with this study was to take the model and just apply it in a predictive way in a hindcast. So like I alluded to, I had been running the forecast while on the ship, but these are actually hindcasts that are based on.
Could you explain that effective? What means? Effective
Yeah, well,
viscosity.
it's kind of a mystery. So basically, it's saying it's not physical, okay? It's an
Because
imaginary thing.
Yeah, on a week ago, I showed the model, and I said the viscosity is due to friction between flows, and elasticity because they compress to each other and they behave. But is it the same? As you said, no idea because
No, it is the same idea, yeah.
Yeah.
the same idea.
It's meant to represent
kind
it,
of-
but in an overall sense. So you have just an ice cover within your grid cell, and you want to say, well, if it is viscoelastic and it's a continuous layer, what would that viscosity, what would that elasticity be? Even though I know that that's not physically what it is. If you take those pancakes out and measure their viscosity, elasticity, you would get a completely different number.
So the kind of in terms of modeling, like a workshop will start next week, multi-scale modeling going from small scale to larger. So it's still missing, right?
Yeah.
Ah,
Yeah.
I think there's a
You
talk
can't-
on exactly on
It's
that.
worse than
Ah.
that. I mean, I don't want to get into this, Eric.
Okay.
We always argue about it, but you can't measure it either. The only way you can measure it is by pumping waves through it and seeing what they do. So
That's
it's
exactly
not a
right.
physics experiment.
So that's
in
what-
true sense.
Yeah.
That's what we call the inverse problem is
But
what.
at
It's
least,
inverse.
it is giving sense to that effective. Right? Even you cannot measure, even you cannot use it to calculate, but
Right.
just giving physical sense.
Yeah.
Instead of saying no sense.
There's a great paper by Keller, who was like one of the leading figures in applied maths, and he worked on the problem. I had the feeling he worked on it for 30 years and realised he was about to die, so he published what he'd done. But he attempted to scale, to calculate the viscosity from these small fragments moving, and it sort of outlines how you can do it, but he got stuck.
Mm.
So
And
it's
he-
maybe not a place to start.
But he only died last year.
Did he? Okay, so he lived longer than he thought.
Plenty of time to sort it out.
Okay.
Yeah, but actually that was a good time to ask that question because, so this is what I call the forward model. The other type of model is the inverse model. And that's what Vernon was talking about, is that you figure out the viscosity by running the model, running waves through it, and you do it inversely. The forward model, by contrast, you just take a wild guess at what you think it might be. Or maybe you have some experience in how this works, and so you use your past experience.
But it's a constant with respect to ice parameters.
Yeah.
No,
Well, it doesn't have to be. So if you're asking WAVEWATCH III in context, it can vary in time and space. The problem is, how do we inform the model about
Yeah.
how it varies in time and space?
And the problem is that those parameters, even if you do an inverse analysis, those parameters change in half an hour.
Yeah.
You know, the
Well,
ice opens
I don't
up.
know about half an hour,
the
but
para-
definitely very
Well,
rapidly.
Yeah, rapidly.
Yeah.
So how do you calibrate it
Yeah.
for every situation? It's
Yes.
very hard to do.
Did you say there was an assumption it was nearly related to ice concentration?
There might have been a slide, but I don't think I said it out loud, but
That's assumed.
that's
Yes.
assumed, yeah, just for lack of any better ideas, that's what we do, yeah.
It looks like everything is rather linear, because you are talking about the spectrum, right? Spectrum, I believe it's linear.
This model,
Idea.
this model is linear because when we change the wave energy, it doesn't, I'm talking about Haley's viscoelastic model. The way we use it now, when you change the energy level, nothing changes. You can make it nonlinear by having these viscoelastic parameters depend on the wave height or the wave period or something like that, or the frequency and the spectrum.
That is so the right hand side, so the fossil term. but the equation itself is linear, and also the spectrum.
It's what I finished on yesterday. The basic assumption in all of these models is the airy wave mode. The airy wave mode immediately gives you exponential decay, and it's a linear model. Everything you do is linear if you start with the airy wave mode.
Yeah,
The dispersion relation, you can't derive a dispersion.
No,
Yeah.
there's non-linear effects in there's a lot of non-linear.
Oh, you
Yeah.
can
Well,
see non.
Actually, you're both right, you're both right.
But,
So the governing equation, the left-hand side is linear. Because
Sure.
the propagation velocities, they don't depend on wave amplitude. Whereas in the real ocean, there is some effect of the propagation of, the wave amplitude on the propagation velocities, and that's what we call nonlinear waves. But the right-hand side is completely nonlinear for
Yeah.
almost all of the terms, completely
In,
nonlinear.
in
Not
some
the
sense,
ice term.
yeah, in some sense it's linear because we are adding term by term. Right? You are adding
Adding them.
term by term. So
Yeah, well,
okay, but each term can be.
yeah, but
nonlinear.
realize the idea of the model is you compute over small time steps. So,
Okay.
it's nonlinear in the sense that you're updating very
So
quickly.
it's the same idea as
Yeah.
used in ship slamming.
Okay.
So slamming is non-linear force, but the ship motion is linear.
Mhm.
So and you combine them, and you kind of two time scale. You use two time scale. One for wave motion at wave frequency, and another one due to the high distance.
Other models, it's weakly non-linear, so you can talk about a spectrum of Volva. If you had very highly non-linear events, then this strategy in WaveWatch just would not work. So the effect of the non-linearity has to be weak.
What type of event are you
If
talking
I get a strongly non-linear event,
like,
like walls hitting, like slamming into a wall.
Oh, yeah, right,
Completely
right.
not working. You couldn't
Yeah,
operate.
right, well, yeah, I think it's generally accepted that that type of situation, it's better if you use a phase resolving model. Okay, so we're still on the introduction, but, yeah, so the meteorological event, so it's basically this enormous low pressure system. So of course, the Gulf of Alaska, the Bering Sea are notorious for monster waves. We were on the north side of Alaska, which is less well known for large waves, but you can see that low pressure system extended all the way up there. So we had this easterly wave event. And so this is the output from the model. So this is a hindcast. And the contours are showing the ice concentration. So you can see what I was saying earlier, which is that the ice is actually retreating over the duration of the experiment. So the white and magenta are showing the ship track, the circle is the ship location. These diamonds are moored locations. This oval is the study area. Color is a wave height, air is a wave direction. So the wave, to answer Pat's question again, the wave heights are up to 4 meters.
What do you mean by retreating? It was drifting with the waves and wind, or
That's
in the
exactly
currents,
right.
or melting?
Yeah,
or
well, there's a little bit of debate about that. So it was definitely drifting, because it's loose ice, as you saw in the video, it's loose ice. And so my gut feeling was that it was primarily drifting. But there is an argument within the Sea State team, which I'm coming around to, which is that there was a lot of melting in place. One argument for that is that because you have the high wind, you have a lot of shear in the water column, which pulls up warm water that's underneath to the surface where the ice is and melts the ice. Okay, so what I noticed when I did the evaluation of the model, that forward model, is that the wave height was very well predicted. So the left panel is just basically a standard scatter plot of the wave height, where green is an open water case completely separate from this experiment. Black is this experiment in the Beaufort Sea. And wave height does very well. On the right, I have the fourth moment of the spectrum. So the fourth moment of the spectrum is very heavily weighted by the higher frequencies. And so it's actually proportional to the mean square slope of the sea surface in a phase average sense. But the point of it is it responds very rapidly, or tells you how well the model is doing in the high frequencies. Whereas wave height only tells you about the what we call the dominant frequencies of the wave spectrum, the energy containing region of the spectrum. So what we saw was that the mean square slope with this model was not good. And so we look further at this problem, and let's see, I'll come back to that later. So, okay, yeah. So what I wanted to mention here is that almost all of the models, parametric models and the physics-based models like the viscoelastic model, they have a common feature, which is that they preferentially damp the higher frequencies. They're basically like a low-pass filter on the waves. And so this is just showing a bunch of different curves from the literature for the attenuation rate as a function of frequency. And you can see that, evidence of that, in images like this, where it's relatively smooth. If you had a picture of a big wave event with 16 to 20 meter per second winds, you would see whitecaps, right? We don't see any whitecaps there. That wave breaking event that Mike noticed, that was strictly because the ship had a wake. Okay, so this is a plot of the energy as a function of frequency. And so for different buoys, we had measurements that indicated different levels of damping of the tail. So in some cases, like the black line, this is basically what an open water spectrum looks like. The frequency spectrum decays at a rate proportional to either f-5 or f-4, indicated by the red and green lines respectively. And so some of them have moderately damped tails, so that would be like the solid green line here, where there's some reduction of the tail. And then some showed, we see in the solid blue line, again I'm talking about the buoy spectra, which is a severely damped tail. Unfortunately, the model always showed severe damping of the high frequency tail. And so that was the reason, that's essentially explaining why we weren't doing well with that mean square slope. And so what I'm going to show about in subsequent slides is looking at the photos that are taken by the Swift buoy. So if you remember that video that I showed in the early part of the presentation about the formation of pancakes, that came from also from camera mounted on one of these Swift buoys. There's one ice observation, quote unquote, per buoy spectrum. So one photo. It actually takes photos much more rapidly than every 30 minutes. But I subsampled into mosaics like this, so this is essentially a 30-minute period. And I take each mosaic that represents a 30-minute period and assign an ice code to it. So in this case, 101 was my code for open water. So this is the mosaic for open water. And this one has a different ice code. So this is I assigned 206, which is pancake and frazil ice. And so then if we take the plots that I showed earlier for wave height and the fourth moment of the spectrum and color code them according to ice type, what we see is the ones that are agreeing well in terms of mean square slope or N4, those are the ones with thick ice. So basically what this is telling us is that our model is going wrong when the buoy is telling us that there's less ice there. And I'm kind of short on time, so I'm going to get to the punchline here, which is basically that we had a crappy ice model. Maybe I shouldn't say that on the video, but we had a good model that was not, it wasn't crappy actually. We had a good model that was ingesting bad information, I should say. So the ice model is actually used by a number of people. So the model itself and the people operating it were good at their job, but they were taking in data through the data assimilation that was not any good. And so that's shown in the gold or the orange lines here. Is what happened is the ice model didn't register the retreat. And so the ice model was continuously telling us there was ice everywhere, when in fact ice had retreated. So the dark blue here is indicating that the cameras on the buoys were saying that this is open water, where the ice model was saying that it's covered with ice. And corroborating evidence, the green and blue contours are from the AMSR 2 passive microwave radiometer estimates for ice concentration.
So what's your color bar, please?
So the color bar is corresponding to these. So the low values mean very little ice, and the high values means a lot of ice. So the ice edge is more or less right here. And okay, so I need to go through this very quickly, but the main problem that we have, again, is with our forcing, because our ice model is assimilating data. It's not very good. So what I did was I decided, instead of using this forward model, the viscoelastic model, where we prescribe the ice and the physics, instead I instructed WAVEWATCH III, we don't know anything about the physics, we'll just treat it as the inverse problem, and we'll run the waves through as Vernon said, and see what the model says about what the dissipation rate should be, given that ice cover. And so the way this works is that I run the model forward with many times, and that gives us essentially a profile for each frequency bin. I get a profile of the mismatch between the model and the observation. So if there's a perfect agreement, it'll fall on the 0 line. And if it's above the line, then the model's too high. If it's below the line, then the model's too low. And this is a function of dissipation rate. So all I have to do is find the intersect for each frequency bin. And that intersect gives me the dissipation rate that the model believes is actually occurring according to the spectra that are observed by the Swift buoys. And so if you take those inversion results and you plot them as a function of frequency, so dissipation rate as a function of frequency, so each one of these lines corresponds to a buoy spectrum. And again, I've color-coded according to ice type, scaled from 1 to 12. So the gold, yellow, orange, those are different levels of open water, maybe with little patches of ice in some cases, but mostly open water, whereas the red lines are the heavy pancake and frazil ice. And you can see that there's a very nice sorting by the ice type. Again, this is using the forcing where the model thinks that there's ice everywhere, but the model is telling us through the inversion process that the dissipation rate for the open water, near open water cases is much lower, and for the pancake and frazil, the profile should look like this. And so that's very encouraging, because it's two completely independent measurements. One is the camera, and the other is the spectrum measured by the buoy, and they correlate very well with each other, as you can see here.
Sorry, this seems really important to me, because so this is basically the attenuation rate extracted from the information, from the measurements, right?
Right. Using the model.
But where does the model come into it?
So the model, it is used in the inversion process. So I run the model, I prescribe a fixed Ki value
Yeah.
and run it through the model. And based on that fixed Ki value, which run from 10 to the minus 6 to 10 to the minus 2 or something like that, then I search for the Ki value for every given frequency,
Yeah.
which gives a match to the measured spectrum
Yeah.
at that frequency.
Yeah. But the Ki is arbitrary, right? You just,
It's not,
I mean, essentially,
it's just you're mapping
Yeah, you're
uh,
choosing
many
the value of
values.
the Ki, which is effectively the attenuation that matches the measurement.
Right,
Yeah.
right.
And because they appear to be straight lines to me, just looking at it. Like,
Which
put
ones
that
are straight
one
lines?
top and the next one.
The next one?
So the KI has no relationship to any ice model. Yeah,
Except that it's using
it's just a,
the ice
value.
forcing that I gave it, which is basically saying there's ice everywhere.
yeah.
And so you're saying these are straight?
Well,
Mike?
it's supposed
Well,
to be-
if you put it on a log scale, they flatten out, right? It just depends on how you plot it. Right?
No, they look quite straight to me.
Yeah.
Well,
Before
well-
you put anything on the logo.
especially if they take too long.
But yeah, so one thing to keep in mind is that because I didn't want to run the model a bazillion times, they are frequency bins of finite size. So there's something like 8 to 10
Yeah.
large bins that I used here. That makes them look more regular than they might if I'd used 100 frequency bins, which would have been impossible actually because the buoy doesn't even give, well, I'd have to interpolate.
But couldn't you take that and just go one stage further and say, here's a formula for dissipation for K, given these, you almost fit to that statistical data, yeah.
Yeah, I'm not sure what you mean. Maybe we could
yeah,
discuss
yeah.
because we're running short of time. But so this is another way to make the same point, which is what I've done here is I've taken each of these mosaics from the photos. So each one represents 1 hour or half an hour of photos, depending on what. I think this is the 1 hour version of this, and I took all those mosaics and I sorted them according to the Ki value at one of the frequencies, one of the higher frequencies. So, and then I played them in order. So it's starting from the one with the lowest Ki value and ends with the one with the highest Ki value. And so this is just another way to reinforce the point, which is that it's not monotonic, but there's a very clear transition from starting with open water, and then you're gradually adding more ice. And you can see that some of the cases that are shown, the frazil ice in between the pancakes are darker. That means it's thinner frazil ice. And the final ones with the highest Ki value, you see it starts to get lighter. And yeah, it looks like slush. And it's really thick stuff like that. And so that's the highest Ki values, which again shows this very nice sorting from two completely independent things, one being the camera and the other being the inversion process. And of course, this paper was published a year ago, almost 8 months ago, 9 months ago. Since then, I've decided that I'm going to abandon that SICE implementation because, like I said, it was ingesting bad data through no fault of the model operator, and instead using Answer 2, which is a passive microwave radiometer, and I see a very similar thing. But you notice there's fewer curves here, and that's because the inversion won't work when you don't have ice. So in order for the inversion to work, the model has to be sensitive to the Ki. If you don't have any ice, the model is not sensitive to the Ki. And so when you do that inversion, you're looking for the intersect of a flat line. The flat line doesn't intersect with that 0. And so you basically get a null answer. So you get fewer curves, but it still shows a very nice sorting. And they are different in amplitude. So basically, I create a step function. So the step function of the new one is shown in gray. The step function from the old result for the pancake and frazil ice is shown in black, but they're quite similar. And so that gives us essentially a parametric model that we can use. It's a step function, Ki as a function of frequency. We can use that in cases where we think there's pancake and frazil ice. And so, and this plot is comparing those step functions, essentially a parametric model for the ice source term, comparing it against some previous experimental results from Mike, from Peter, and from Haley's viscoelastic model.
So does the parametric model go as frequency squared?
I don't know, but we can try to figure that out.
That's what I'm wondering. Look, if it was a straight line, it would be that.
No.
But it
Because
seems
that's what's
to
been observed
flatten
before.
out a bit more than like Haley's model.
Oh, sure.
And so that's perhaps one conclusion that we can draw about the viscoelastic model is maybe it's a little bit too aggressive as far as damping the shorter waves. So yeah, I'm going to make this. Okay, so I'm getting close to the end, let's say. And this is a mystery to me. So this is actually suggested by Jim Thomson and his student, Manny Smith. But, so they had the ADCP, I mentioned the ADCP on the Swift buoys. So it's a downward looking, is that right? No, this one's the upward looking ADCP. It measures a TKE dissipation rate in the water column. And so I took their measurements of the TKE dissipation rate. So that's plotted as a function of vertical distance. And I've used, again, my color scheme, which is according to ice type. And again, you see a clear sorting of the dissipation rate. So this is basically the turbulence in the water that is measured by the ADCP. And it's still a mystery as to why this is. Intuitively, it seems to be like we're dealing with different flow regimes here. And in open water, of course, you have white capping. That's the traditional mechanism for generating TKE. You get white capping, and that's always very close to the surface. But the weird thing is, why is the ice, the dissipation with ice cover further down the water column? And I don't have a good answer to that.
But how
Because there's
thick
a
is,
boundary line.
yeah, how thick is the layer of greasy frazil
Uh,
stuff? That'll
it-
damp it at the top.
Yeah, so that is at most 15 centimeters, I would say, or 15 to 20 at most, but sometimes it was only 5 or
So is that left-hand scale just meters?
yes.
So that's
So it's significantly lower than the
half a
ice.
meter, yeah, half a meter down.
Yeah,
Oh, half a meter, shouldn't it?
No, that's not very much at all.
right.
A minute.
Not much.
Okay, so I don't need to read through these, but oh yeah, so this is definitely my last slide. One thing that maybe I could discuss with Vernon, and we touched on it a little bit before, is that one thing that's obvious that comes out of this is that in order for the formulation for dissipation by the ice, in order for it to be accurate in a forecast sense, or even in a hindcast sense, we need to know the ice type. We need to know the character of the ice, which is, of course, our most difficult problem. And so the question is, it seems like the viscoelastic model and the parametric model, they both have this limitation, right? And so then one could argue that if the parametric model is much faster, much simpler, much more robust to compute, then what is the advantage of the viscoelastic model? And one that I can think of offhand is that, well, at least it's something that can use the ice thickness that we're getting out of our ice model. So that's one advantage, parametric models, they don't typically take into account ice thickness. That's just something I'm wrestling with, does it make more sense just to essentially retreat and use a parametric model as opposed to using this physics-based viscoelastic model?
It's not physics-based.
Well, it's based on physical principles, right?
Applied from another.
But
All right,
now
well, you
I
said
mean, that's
that,
like
you said that, I
saying-
didn't.
That's like saying, well, it's like the discussion we had yesterday about exoplanets.
Yeah.
We've got a nice model of an exoplanet, but we'll apply it to sea ice.
Mhm.
I mean, that, yes, it's based on physics, but it's not based on the same physics.
But,
Okay.
one of the things that's missing when you show those, comparisons is the results that Martin had where he found for pancake ice in the Antarctic, he had this linear proportionality with thickness,
Right,
and then,
right, we didn't have good estimates for thickness.
but I wonder whether, because it would be interesting to see how closely those results lay with what you found.
Oh,
right?
yeah, I agree.
Because, it's much more similar conditions, right?
Right.
Whereas the stuff that was done, your Allison version, that was at the end, the ice was much, much bigger and tougher. And the attenuation was correspondingly way bigger, right? Stretched. But it was still, a similar slot, on a little, you could put it on a similar curve maybe and just shift it.
Right.
The analysis that Fabian and I have done with this data, this experiment, suggests attenuation coefficients around 10 to the minus 6. So I don't know what Martin is.
Well, that's what, that Ki is the attenuation coefficient multiplied by 2 pi or something, right?
Yeah.
If you had e to the minus,
It's alpha over 2.
Oh, alpha
So it's
over two.
energy
Oh, so it's
dissipation rate
energy.
divided by 2. So Ki is amplitude dissipation rate.
isn't there a 2 pi or something?
No, there's no
not.
2 pi.
No, of course it's okay,
No.
yeah, all right, yeah, no 2 pi.
Well, it depends with,
Yeah, so it is just our alpha, mostly scale. I don't understand that picture seemed really important that they taken with looking down the profile. That's showing you where the energy is being absorbed
Yeah,
in the
that-
fluid.
Yeah, it's just fascinating, but I don't have a good explanation for it.
So what
But
is,
maybe Pat does.
but can you just explain to me what that says? It says, I'm gonna go down through the fluid and see where it's getting heated up by some process, is that right?
Well, that's what I wanted to ask, how can it see through the frazil lines?
It's upward looking. So they've got this spar buoy that's down the water column, and then they've got an ADCP mounted on it,
Yeah.
and it's looking up.
But
At the
didn't you say
turbulence.
there was 15 centimetres of frazil?
Yeah,
And
it's
yet
not
there are
looking,
plots.
that
Yeah,
frazzle
so
ice
it's
is
not
at the
at the
top. It's not looking through it. So this is all water. So it's looking up through the water.
Yeah, sure, but didn't you say, I mean, some of the pictures you showed,
Huh?
it was very white on the top.
Yep.
So there was this soupy mess.
Yeah,
At the
but
surface.
again, I
And-
think it was about 15 centimeters at most.
But 15 centimetres would be,
Yeah, right here.
yeah, and you're seeing up through that.
Oh, yeah.
That's what,
Yeah, who
that's
knows?
what I'm
Yeah, so,
confused by.
no, I agree with you. So that would be the red lines, because that's the thick pancake and frazzle. So if this, I don't know, 15 is the highest value that I think
Right.
that existed. So I would say you're right that some of these red lines, you had ice down to 15 centimeters. So yeah, what does that mean? I don't know.
Are you asking how are these measurements made?
No, just curious about, because this is telling me that the energy's been absorbed below the ice some distance, right?
That's exactly
Is that what it's
saying.
saying?
Well, there's turbulence in the water, and it's going to heat at some vertical level.
And that level, that's really interesting. I mean, that level is half a metre below.
So what could that be? If that's the
Well,
dominant
that-
mechanism, then we're miles away from it.
Well, I mean, like Vernon said, there's gonna be a boundary layer on the surface. So the ice is stopped, roughly, which means that it's kind of it's like a flume, it's like
Yeah.
a pipe flow.
So
Or
the-
not
yeah.
pipe flow, but
Yeah.
it's channel,
So
so
the
you've
top
got,
fluid's stuck on the ice and can't move, and the bottom fluid's moving with the weight.
well,
and
it
then
will be,
grinding.
it would be stuck, but it will be moving with the ice. It's
Yeah.
moving with the ice,
You have
and the
a
shear
a
is
boundary layer,
underneath.
a laminar laminar layer, essentially.
So why do you say there's turbulence? Is that a fact? I mean, you know that, or is it a guess?
Yeah, well, no, the ADCP,
Yeah.
that's what it measures,
Yeah, I
it's the
see.
TKE dissipation rate, not the turbulence, but the dissipation rate of turbulence.
I see.
It will definitely be.
So can you go back to the picture with all of the
It will be
attenuation models
untidy.
and the rates,
Right.
just like, you know,
It
you-
will
they
be
put that one
messy,
there.
But why do you say there's definitely turbulent?
If you say that it's
Because-
linear with wave thickness,
Because
ice
it's
thickness, then the
waves.
measurements in the
Because
Antarctic
you're
are
really
going
close.
to
The waves seem
be
pretty
15
regular, right?
centimeters. You can bring that
Ah,
down by,
I'd be
the curves would start to colourless along
I'm
the way.
fairly convinced.
That red one,
So that would help us a lot if we could generalize this, if that's where you're getting
I
at.
think it's.
Sorry, Mike, what did you say? I was listening to my wife.
Yeah, we've got two
It's very
sides.
rare.
I wish I could achieve that. I was just thinking that it's linear with, if it was linear with thickness, then that red thing, obviously the ice was way thicker, so that would bring that curve down much closer to the other. Right?
Which curve, sorry?
That red one,
Oh,
isn't it? Because the ice was much thicker in the Antarctic, that's from, it'd be great to see
Yeah,
these results.
or if you do the reverse and say that the new line, the purple line is associated with thin pancakes, thin frazil layer. If you could build in something to generalize so that you can plug in a thickness, and the higher thickness would maybe bring you up to the red line.
Yeah. But the
But
measurements, see with
That
mountains-
model, that Naval model was just scattering.
No, measurements. Nothing, it's not a model, it's just,
Oh,
it's just
okay.
what the,
It's
what
measured.
to measure.
Okay, it's not Allison's.
Remote model, no,
No,
it's just the
no.
measurements, yeah. And it's,
So was that the T to the 2?
yeah, it's
T
T to the minus 2, I don't know, I think the T,
Oh,
it must be a T to the 4, because it's what's given.
yeah, well, the T to the 4's
But
a little tweak, but it's-
Martin's measurements would also lie somewhere on that, with, and they were pancake, which is much more similar. It'd be interesting to see whether how that all lines up. Because if there was some, hopefully there'd be at least some consistency.
See, I'm looking at a different approach entirely, which is kind of like your parametric approach, and that is forget all of the models and just think about a system where your viscosity is proportional to strain rate in some way. And you can tune it so that the viscosity is proportional to strain rate in a way that gives you the T to the 2, or the T to the minus 2 relationship. And when you plug that in, you get that curve.
Yeah.
It's quite clever.
And then you've got one parameter to tune.
Yeah, really, one parameter, that's right.
It's all the fudge.
It's a fudge, yeah, but, you know, these are all fudges,
That's the
really.
world we live in. We have a parametric model, or we have a viscoelastic model that's based on what you say is not physics.
Can I ask, I'm interested that in the plots we've seen so far, nobody has the frazilized measurements that
That's
were
what,
taken,
this
the
satellite?
the University of Washington frazilized damping, precise damping experiments
Oh,
that
well,
were
they
done.
do.
Is this a lab experiment or field?
Uh-huh, a lab
Well,
experiment.
Keller also had a
Keller's-
lab experiment. That was the earliest, I
Oh,
think.
right.
That was the same. Keller worked with Stephen Martin.
Oh, was he
Oh,
at
did he?
University of Washington? Is that what you-
No, he was at Stanford, but the two of them worked together.
All
Okay.
right, sorry, I'm the way.
But it would be useful to keep adding to this picture, adding to more.
It's a way of keeping the funding.
Yeah.
No, like all of these,
I've been doing this for 30
We only
years and the
know-
problem is still active.
we actually know half, each of us only knows half the measurements.
Right.
Anything about these waves.
Sorry?
Excuse me,
Right.
it's 40 years.
40 years.
Yeah, you can make a very busy plot like this. And we're adding new curves. And, you know, Alex Bobanon's flume, he's doing measurements, the one that you brought up yesterday, that people are adding new ones.
Well, Keller's model is just a viscous model. It's a viscous layer
But
model.
it doesn't sound like you needed the elasticity anyway, you didn't use the elasticity to zero.
Well, because I had no idea what, okay, there is a slide, and, yeah, I should apologize for not doing much math here, but this is what you get when you invite an engineer to a mathematics meeting. sorry. Well, anyway, there's a plot that I made where I did play around with different viscosity or elasticity values. And basically it was just to make the point that one problem with the viscoelastic model, at least in the previous generation of it, was that you have this mode jumping that Vernon discussed. And so if you plot it as a function of frequency, and the plot's in my paper as well, you get this, it's not this nice monotonic curve like we see in the measurements, or well, all those curves that I was showing. Instead, it kind of zigs and zags. But yeah, in principle, it's possible to add elasticity. And the reason why I even tried that is because, like I said, Haley's model, it's a little bit overzealous. So that's the green and the blue lines there. It's a bit overzealous at damping the high frequency. So I thought if I add elasticity, I can pull that down. And it actually does pull it down. But the problem is then you get this mode jumping problem because it's now a viscoelastic model, a proper viscoelastic model. But that is something that Haley's been working on, and so that might be resolved in the present version. And of course you have competing versions, Vernon's famous IC5 mechanism. Which he's put into WAVEWATCH.
What we're talking about, Sasha, is that my model was originally developed just for waves entering a plate, what I talked about at the beginning. And Haley's idea was that she would combine the viscous models, which Keller developed, and the elastic model, which I developed, by making a viscoelastic layer model. And she solved that problem. It's a nice mathematical paper. Independently, we put some viscosity in the thin plate model that I used, but that's still a thin plate. So the thin plate produces very simple results, but the viscoelastic layer model is very rich in terms of the wave modes that it can actually sustain, including both flexural and longitudinal type waves, pressure waves. So that's what the mode jumping that Erick's talking about. In Haley's model, it'll be happily trundling along and suddenly it will jump into a longitudinal mode or some other mode. And Haley found a slightly dubious way of joining it all together and producing nice results, but the waves themselves are quite different waves. Whereas the simple model replicates a lot of what Haley does, but in a.
Are you talking about
It doesn't have so many.
the Fox and Squire?
Yeah. Fox and Squire with a bit of viscosity.
Yeah. So what happened is Vernon provided us with some MATLAB code, and one of Alex's students, Chin Shan, he's put it into WAVEWATCH III. So we have two different viscoelastic models to choose from.
Yeah. And neither of them are any good. Well, as I say, they were developed for completely different things, and that's what worries me. We're using it outside of its design specification. And the other big problem here is that, as I said to Alex, when they actually run the model, they have the parameter space. If you take the simple model, the parameter space is still very large because you can have pretty much any viscosity you like, and you can have any elasticity you like. So it produces some very strange results, as you might expect. If you model the marginal ice zone like a titanium plate, you get very odd results. And you get things like the group velocity jumps by a factor 10, which of course is complete nonsense. But that's what worries me. We're pushing those values too much. Ice is not, the maximum ice value that you would ever get for an ice plate is about 5 times 10 to the 9, 5 gigapascals. And, the last run I saw was up about 10 to the 12 gigapascals. Well, that's like steel.
Yeah, steel.
You know, you've got steel sitting on the surface and you're expecting ice to behave like steel. It just doesn't make any sense to me. That's why I'm worried about that elasticity particularly. I'm less worried about the viscosity. So I was quite pleased to see you actually knew that for this analysis you
Right.
knew the elasticity to
Right.
look at what the
It's
viscosity did.
really, like, sorry to interrupt you, but look at that like, the thickness in the Antarctic, nobody measured it, right? I'm guessing it'd be about half a
Half a
metre,
metre.
roughly, and the thickness here was what, see?
15 centimeters at the most, but
Yeah, because so that would, so you divide by a factor of say 4 or something, which would pull the curve down to the low scale about that much, and that red curve would just start to line right up down here. When that red curve, so it's like the same mechanism is causing the attenuation in the Antarctic and in this situation, like, which, when that,
No reason why it shouldn't.
yeah, but what is that mechanism? It's certainly not scattering then, right? Because
No,
there's no
it's
way
not
these flows are
scattering.
scattering.
Well, the
Some layer effect.
TKE gives you the.
Yeah, exactly. Some boundary layer. That's
some boundary
well, I
layer.
think
it's dependent.
I believe it's going to heat somehow. It's just a matter of where it's going to heat. Is it like a porosity effect within the frazil that's causing friction, hysteresis, or how do you pronounce it, Vernon? Is that right?
Hysteresis.
Hysteresis.
Well,
Yeah.
Oh, history.
Wow, that's a really bad pronunciation. You don't even know what I'm
Depends
saying.
whether you're American and you say buoy or you're English and you say boy.
Right. But anyway,
Hysteresis or
I
hysteresis.
think it's going to heat. It's just a question of, is it in the ice itself, on a molecular level?
Yeah.
Or is it in the gaps between the ice, or is it under the ice where the heat is occurring?
Yes.
Yes.
What are you saying, yes to? Pat? You think it's under
All
the ice?
three. She
They're all
was being
three.
funny.
It would not be
I think the answer to that is yes.
It'll be everything. It is interesting that it's so dependent on thickness because sea ice doesn't actually do a fabulous job of thickness as
The size model.
do size
Mhm.
or any of the other
Mhm.
ice models.
Right.
I mean, it presumably doesn't get 193 meters. We looked at some models recently and one of
Right.
them
Right.
predicted 193 meters for sea ice somewhere, which is
A
clearly
glacier.
not correct. So if it goes, what did you say as h squared, Mike, what did you say? H something?
T
What-
squared, with minus 2. So frequency squared.
No, but what about thickness
Linearly
dependence?
with it, yeah. But
Just
that's-
linearly with
but-
thickness?
It may not be entirely linear because, you know, they only had measurements for small targets, right? Yeah, so,
Mm.
but it was the strongest determinant of it, thickness.
Yeah,
Can I ask
Luke.
one slight question? What was wrong with the sea ice model?
Okay, maybe I need to turn off the.
Alright.
So
I'm talking
yeah,
sort of
there's an interesting story to this. So the size model, of course, you have to assimilate something into it, and the simplest thing to do probably is to assimilate passive microwave radiometer from the satellite because that's something that's rapidly available in real time. The Navy has determined that they'd actually like to use something better, which is SAR. So SAR it actually gives you a better estimate of where the ice edge is than passive microwave. Passive microwave has some problems. Sometimes the ice will show up as open water, especially with melt ponds in the summertime. The passive microwave has problems, so they want to circumvent by using the ice edge that's from the SAR. And the question is, how do you get ice edge from the SAR? So the NIC, the National Ice Center, they actually have analysts that go in by hand and draw out the ice edge using the SAR image. And someone clever has taken those, essentially their shape files or vector information and converted it into gridded product so that it can be ingested into the wave model. So you basically have a gridded product that includes the ice edge, and they can take that into the data simulation. So it's actually very clever what they've done as far as the technology.
So it's not an initial condition.
It actually is. Well, the data simulation is changing the initial condition. So that's what the data simulation is doing essentially.
But then the ice model takes over from there.
And then the physics of the ice model
So-
takes over, or physical parameterizations.
It's not predicting the retreat of the ice edge correctly. Is there a time lag?
But the problem is not the physics. It's, again, I'm
So
not
very
really,
confident about that.
no, it's not. The size model itself is not to blame here, and the person operating it is not to blame. What happened was that you have a human involved in drawing the ice edge based on these SAR images. And what happened is they didn't update their drawings. I'm using layperson's terms, I don't know the correct terms, but they didn't update their ice edge drawings for 3 days while this wave experiment was happening. And so essentially that ice edge for the initial condition, based on the SAR imagery, was using an old SAR image when the ice edge was back in its old position. So it never retreated. So what would happen is, every time you run the model forward, the ice model would want to have that retreat, but then you go to the next cycle and the data simulation forces it back to the wrong position because the data simulation hasn't been updated because the analyst made a mistake or maybe overlooked a newer SAR image. And so what the solution to this is, what they need to do is to have metadata associated with that gridded product which says this ice edge is 3 days old, so that the ice model knows not to use it. Ice model can use answer 2 instead.
It wasn't Thanksgiving or anything like that.
Well, you know, one hypothesis, and this is not something I'm sure about, but there's one hypothesis, is that there was an analyst that was an expert for that region working at the NIC. They got pulled off to create a specialized product just for our crews. But because that person got pulled off, there wasn't a so-called expert to do the existing product, which is the one that's used by the ICE model for the data simulation. Again, that's just one hypothesis for what happened.
So apart from these hypotheses, right? One thing is, you know, the outputs from the size model are very important. Be a wave model. How you've shown that, and if you gave it the right input data, then the sea ice model is doing a good job of telling you where the ice edge is, even though the rheology is probably not developed for pancake ice like you're seeing there.
Right.
And during strong storm-like conditions.
Right.
Strong winds.
So I think in the ideal scenario, we have a model like SICE, which either produces information about the ice type itself or informs some intermediate toy model or whatever that can tell us, okay, it's probably frazil ice, it's probably pancake ice. Pancake ice is forming, pancakes are decaying, or it's flows that are breaking up. But it could use context clues about like the sea surface temperature, the history. So you could build something that would tell you the ice type.
And how often do you couple?
How often do we couple?
You know, how often do you take that snapshot of the ice to then put the waves through?
Yeah, it depends on how you run it. So if you're doing it in a hindcast mode through files, usually when we're dealing with ice input, it's every 3 hours. Or meteorology, it's every 3 hours. So we'd probably do that. But actually, in the technology that's being developed now, it's at every model time step because it's done through system memory. And so all the models are running together in lockstep. So so we have that running now with ice, ocean, atmosphere in a kind of experimental fashion, where everything is changing and running together. And so that's kind of like the future as far as running. And the waves will be part of that.
Rapidly there in the early shots that you show.
Oh yeah.
Anyway, we're going to talk about waves at this sea ice Broke from there.
Sorry?
I said,
Oh, now you understand.
All right, so I'm gonna